In the last few lectures, we have discussed about basis sets, how they are constructed, what is their nomenclature and how to count the number of Slater and Gaussian type of functions. And we told that the methods, electronic structure methods can give good results only when you are using a very large basis set. And in today's class, we are going to learn about one of the problems what will come if you use a small basis set, and that is called a basis set superposition error. For example, let us say I am calculating binding energy of a subsystem. So, let us say I have two systems A and B. I am adding them together to make a super system. Now, of course, I have individual basis function for A and B. What happens is that when I combine A and B, the total number of basis function is actually much larger than A and B individually, because now I have the basis function centered on A and basis function of centered at B. So, that means in this complex, A actually sees not only the basis set localized on itself, but also the basis set which is localized on B. Similarly, B sees the local basis set which is localized on itself as well as the basis set localized on A. And this actually leads to much larger basis set than isolated subsystem. So, what will happen is that the energy of AB inside the complex will automatically get lowered than what is their energy in individual A and B. Remember, this lowering has nothing to do with the interaction among themselves. This is not the physical interaction, but this is the size of the basis function of what each of the fragments is individually seeing. That means, if I have two monomers A and B which will form a dimer AB, then the description of A in the complex AB can be improved by functions of B, and the definition of B can be improved by functions of A. But this extension is not possible for the calculation of isolated A and B. So, that means when I am doing the calculation of A and B, let us say A have a basis function of 2s2p and B has a basis function of 3s3p. Just I could have taken any number of basis functions. I have just taken 2s2p and 3s3p as an example. Now, if I have this kind of a basis function, so that means my basis function on AB is actually total addition of 5s plus 5p. So, if I am calculating the interaction energy, then basically what will happen is that my energy of AB is calculated at 5s 5p basis set, whereas the energy of A and energy of B has been the energy and both the energy and geometry. For A it is optimized using 2s2p and for B it is optimized and the single point energy has been calculated using 3s3p. So, this leads to something called a basis set imbalance. How we can correct for it? If we discuss the uncorrected interaction energy between monomer A and B as E interaction AB is equal to, before going into this kind of structure, let us see the nomenclature. So, what is inside the bracket is the basis set, what is superscript is geometry, and which is subscript is the system. So, this essentially means system AB at the geometry of AB and the basis set of AB, whereas this means system A at the geometry of A, basis set of A. Now, we can attempt to correct this above equation by estimating the amount by which monomer A is artificially stabilized by the extra basis function coming from the monomer B. This is how it will look like. So, here you see the same things are calculated, one with the basis set, complete basis set of AB, and the other one is only with the basis set of A, that we will call as a BACC energy of system A. Similarly, for the second system, what we will see is that the BACC of B will be energy of the system B calculated the geometry of AB and basis set of AB minus energy of the system B calculated at the geometry of AB, but only with the basis set B. So, to correct for the BACC problem, what we use is the Boas and Bernardi counterpoise correction, and what you do here is that the energy of the monomer A in the dimer basis must necessarily be lower than the energy of monomer A in the monomer basis, because my basis set dimension of has increased in the dimer basis. So, the energy will be lower and thus the BACC of will be less than 0. So, the error is actually stabilizing. So, if we subtract this error from the interaction energy, this is what the formula of the counterpoise correction will look like. So, what we will do here, we will perform calculation on a system, and then we will see how much is the individual energies are and how much is the BACC errors actually is. So let us take the example of a water dimer. We have still not came up to the discussion how to do geometry optimization. So I am still providing you with the optimized geometry of the dimer and optimized geometry of the monomer. What we will do here, we will perform the individual calculations and actually then calculate the BACC counterpoise correction. Of course, what one can do is that one can actually make input file for all of the system we need separately, and just to show you what are the things we need, let me increase. Maybe not so much here. So you need to calculate all these quantities, and of course we can make separate input file for all of them and then calculate it one by one, but the ORCA compound job feature actually allows you to perform multiple calculation using the same input file. And if you go to this link, you will see how the compound features actually look like. So the compound job will start with a block percentage compound, and then for each job you have to use a command called new step and then step end, and when all the job actually ends, then you have to use something called an end run. So we are going to use the same format and actually going to prepare all our input file for performing the counterpoise correction. It may happen that if you prepare this input file for the first time, it may not run because there may be here and there typos and correction should be needed to do this kind of correction, and even when I will do the calculation it may happen, but eventually if you correct it all the things, the advantage is that same job will give you everything is needed, and basically you can automate many of your calculation using the compound command. So let us try to do the compound command for counterpoise correction. So let us go to Notepad. Okay, let us start it. So I will do some copy pasting here. It's a good idea to put command on every line. So I will start with, so first thing I would need energy maybe I can increase the size a little bit more. Energy of AB on the geometry of AB and also in the basis set of AB. Then the keyword is new step. My geometry of the dimer is given here. I have to put the spaces here. I have not put the method. So this is the method I should have used, and this is we are going to use for everywhere. So, this is a restricted Hartree-Fock calculation. MP2 is a molar placet perturbation theory. We have still not learned about it. In the next week, we are going to learn about it. Def to SVP is a basis set. We want our SCF calculation to be type. XYZ file actually writes the XYZ file in the individual geometry in your disk, and actually the P model actually gives you the corresponding calculation for it's basically the guess for the Hartree-Fock. So, for the so it will start with, that every SCF has to start with a guess set of orbitals, and this uses P model guess for the SCF orbital. Now, this is done my calculation. So, I have to end this step with the command step end. So, once you make one of it, we can just copy paste for the next one. So, this is the first thing we needed, energy of the system AB at the geometry AB and basis set AB. Next thing, we would need the energy of A, and at the geometry A when with basis set A. The advantage is that here my system is monomer. So, both the monomers will have same optimized geometry. So, I can do this calculation only once. If your A and B is different, then you have to do this calculation twice. So, I can just copy all of it. So, the next one will be energy of A with the basis of A and geometry of A. Everything else will remain same, only I have to change this part. So, I have to take water optimized geometry. So, the next information I would need is energy of A at the geometry of AB and basis set of AB. So, how one can do that? Let me first copy this step. So, I need energy of A at the geometry of AB and basis set of AB. So, to do that, what we need to do is we have to make sure that only the basis set of AB has been present, not the electronic structure of B. So, we can make it by using a command called ghost atom. That essentially means I have to put this colon after this. So, here the first two oxygen and then 2 hydrogen of the first oxygen and the 2 hydrogen of the second oxygen. So, if I put this colon, this oxygen and hydrogen of the second water will become a ghost atom. What does it mean by a ghost atom? That means it will have the basis set corresponding to these atoms, but not the electrons or the wave function. So, that means now it will become energy of A at the basis set AB and geometry of AB. So, the next thing I would require is energy of A at the geometry of AB, but now without the basis set of B. So, I will again paste the same thing. I should put a space. So, now this is energy of A at the geometry AB, but basis set of A. For doing this one, I need to delete that. atoms of corresponding to the second water. Okay, I am doing it for such a long time, it is a good idea to save it. I need to make a new folder called BACC. And I make this file name as CP to tell that it is a counterpoise correction, and I make it cp.inp. So, the next thing I would need is energy of the system B at the geometry of AB and with the basis set of AB. So, again do the copy pasting. So, now this is energy of system B at the base at the geometry of AB at basis set also is AB. So, that means now I have to make the atoms of the first water molecule as ghost, the atoms of water A, if I call it this space. And the next thing, so now I would make it energy of B at the geometry of AB and basis set of B. So, I have to remove the coordinate of first water molecule. So, now my compound job is almost done. Only thing I have to end the compound by end run. I am doing it for counterpoise correction. You can do it for many other kind of jobs also, if you like. So, let us run it now. I go to open the terminal. Sometimes it happens that the PowerShell does not show up automatically. Now it will show up, I believe. Open in terminal. So, if your PowerShell is not automatically showing up, you just open the PowerShell once and it should show it up. So, we are there. So, it is orca cp.inp, cp.out, brace for the impact. It is running. So, just do it very carefully. It may happen that you have make a mistake, so it will not run properly, but if you do try it few times, this is definitely going to work. And once our calculations are done, we are going to copy paste the energies one by one and then put it on an Excel sheet. So, I have prepared an Excel sheet where I have written all the quantities so that I can count. You have seen that we can, by using this Excel sheet, we can perform these calculations quite easily. Just maybe I want to insert another column where I want to write the basis set. So, these calculations we are doing at def to SVP. Okay, while discussing, we have discussed interaction energy. Here I have written a binding energy. So, there is a very subtle difference between binding energy and interaction energy. I am not going to tell what it is. Please go to the Google and search it and find out what is the difference between binding energy and interaction energy. So, my calculation is done. So, it says start compound job 1, so this is the SCF energy, and this is the MP2 energy, and this is my final single point energy. So, let me copy it. And put it on the Excel sheet. So, this is energy of the AB system at the geometry of AB and basis set of AB. Now, compound, this is my compound job 2. Do not forget what was there in the compound job 2. Oh, it is on this one. Energy of A at the geometry of A and basis set of A. So, I quickly can also use the search option to be a little bit faster. So, this is energy of A, this is energy of B, because A and B is same here. So, I can use the same one, and this is what I can calculate as my, oh, this is, I forget to put the, copy the minus sign, this should be fine. This field I have made some mistake, no problem, I have it on the top. So 152.328. Put a minus sign here again. Of course, this is in the electron volt, sorry, this is in atomic unit. I should make it kilocalorie per mole. So, it is 7.32. Now, let us see the, if I, so this is the binding energy without any correction, counterpoise correction. Let us now put the other quantities. So, then we will see what is the magnitude of the counterpoise correction. So, this is the energy of A at the geometry of A. So this is compound job 3. See the number of electrons. Although it says 6 atom, the number of electron is 10 because it's only one water molecule. Now next is energy of A at the geometry of AB and basis set of A. Of course, this energy will be lesser than the previous one because previous one was done with the basis set of AB. You see this energy is slightly less, and now we are left with only two more. The energy of system B at the geometry of AB and basis set of AB. Remember, this will not be same as the energy of A at the geometry of AB and basis set of AB because A and B geometry will be different. Again, I am not taking the minus sign somehow. Copied it. The last thing I require okay. So now let us use the formula. Energy of B, energy of this one, energy of A at the geometry of A, energy of B at the geometry of B. Then I need to put a bracket inside the this minus this plus energy of B at the geometry of B, AB and basis set of AB minus energy of system B at the geometry of AB and basis set of B. This is there, and of course I need to convert it to kilocalorie per mole. I have to give the multiplicative sign. So you see the bonding energy with counterpoise correction actually is slightly less. Of course, slightly less means it's actually 3 kilocalorie, which is outside the which is much more than what the chemical accuracy will get. So at def to SVP, the energy of counterpoise correction is quite high, 3 kilocalorie per mole, and you see if you do not include the counterpoise correction, it can lead to artificial stabilization. More minus means the complex is more stable. So this is we have shown with def to SVP. So your homework problem is to perform the same calculation now with a much larger basis set def to QZ VPP and see how much is the counterpoise correction changes in that case. So here we have discussed about BACC correction. We are skipping the issue of complete basis set limit extrapolation for the time being, because before going there you need to know about electron correlation method, and once you know about electron correlation method we will come back to this problem and we will see how one can extrapolate the smaller basis set calculation to the complete basis set limit.